Hi everyone, I'm Amirali from UC Berkeley. Today I'm going to talk about our recent algorithm called BEAR for feature selection in ultra-high dimensions. In 2020, about 4 million Google search queries were made every 60 seconds, generating a large volume of high-dimensional data. The data has also been growing in areas such as genomics, networking, and language processing. Putting this rapid growth of data in contrast with the now slowing trend of Moore's law, we can safely claim that the only way to tackle the next generation of big data problems is through developing more scalable algorithms that work under various resource constraints. In this talk, we consider the feature selection or Cullen subset selection problem. We assume we are given n data points with input features xi and output labels yi, where xi lives in an ultra-high dimensional feature space of size p. Our goal is to find a small subset of features that best predicts the output label from the input. We also assume that the output can be captured using only a small k number of features encoded in a p-dimensional feature vector called a beta star. Given a loss function f, we like to minimize the empirical risk to find beta. We know that when p is sufficiently small, this problem can be solved efficiently using stochastic gradient descent over a mini batch of size b. Now the challenge is that while the final feature vector beta star is indeed sparse, the vector can get dense in intermediate steps of the optimization algorithm. However, due to the sheer dimensionality of the feature vector, or limited local computing resources available, we do not afford to save a dense feature vector of size p in the memory. So how can we compressively solve this optimization problem? In particular, can we solve this problem with memory that grows sublinearly with p? One workaround is to use a data structure from streaming literature called count sketch, which is used for counting a large number of items using sublinear memory. Count sketch randomly hashes p items, in this case cars of different colors, into a smaller number of d bins or buckets using multiple independent and random hash functions. Of course, in general, this creates collisions of cars with different colors into the same bin, which causes information loss. However, assuming that there are only a few highly frequent items, then we can safely say that these so-called heavy hitters won't collide into the same bin in the majority of hash functions. Therefore, we can query back the value of the top items by simply looking at the median of the bucket values each item is being hashed to. In this example, every time a car passes, we increment the buckets associated with this color by 1. And at any time, we can query back the count of each color by taking the median of the values associated to their 4 bins. Now the question is, what theoretical guarantees do we get using count sketch? We can show that count sketch preserves the number of occurrences of the top k items using a memory that grows only logarithmically with the total number of items. And naturally, we need to assume that the energy of the non-top k values are sufficiently small. Otherwise, we will have to allocate more memory in order to store them. Okay, but how can we use count sketch for feature selection? Recall that in the feature selection scheme I described, we would like to do stochastic gradient descent on the loss function f. The idea is that instead of adding up the stochastic gradients in a p-dimensional vector beta t, we can store them in count sketch, and count sketch will eventually recover the top k important features. In order to do so, we simply replace the cars in the previous slide with the coordinates of the non-zero gradients and increment the associated bins with the value of the gradient at that coordinate. In fact, this is the idea behind an algorithm called mission published earlier in ICML. Okay, but what is the problem? The key observation that we have in this work is that the sketch of the noisy component of the stochastic gradient descent, which normally cancels out when we don't do sketching, gets accumulated in the count sketch, as you can see in the plot on the left. This unwanted sketch noise negatively impacts the feature selection performance of the algorithm. And therefore, if we somehow get rid of, or at least reduce the noise, we can potentially select more features using a smaller count sketch, which in turn enables a better memory accuracy trade-off. But how can we reduce the noise in a stochastic gradient descent? So the key idea behind our Bear algorithm is to hash the second order gradients instead of the first order gradient in the count sketch. Of course, we need to pay a bit more computation time to find the second order gradients per iteration. However, in return, we will put the available memory in a better use by reducing the sketch noise in count sketch. In fact, in practice, we observed that the total convergence time of the first order algorithm, the second order algorithm Bear and the first order algorithm Mission are in fact comparable. But now the question is, how can we estimate the inverse Hessian in a computationally scalable manner in such a high dimensional space? Fortunately, there are second order algorithms developed in optimization literature which avoid counting and storing the inverse Hessian directly. Some of these algorithms approximate the Hessian as a low rank or diagonal matrix. However, the complexity of all these algorithms grows at least linearly with a problem dimension, while we only afford a sublinear growth in memory. In this work, we leverage ideas from a limited memory BFGS algorithm, which directly approximate the inverse Hessian times the gradient using the gradient difference vector from the last tau iterations. Importantly, there won't be a need to explicitly store or compute the inverse Hessian. Bear iterates between these two key steps. One, finding the descent direction using the LBFGS algorithm, and two, querying count sketch in order to monitor how much the gradient has changed with respect to the feature vector in order to estimate the inverse Hessian in the next iteration. Bear also employs an efficient heap data structure in order to maintain the index and value of the top k elements. We analyze the convergence of Bear under three standard assumptions, which is gradient being bounded and bound on the eigenvalues of the Hessian matrix. So the convergence analysis of our algorithm showed that Bear retains the 1/t convergence rate of the LBFGS algorithm in the sketch domain. In addition, the memory complexity of the algorithm grows only sublinearly with the problem dimension, and the computational complexity grows quadratically with the sparsity of the data per iteration. To the best of our knowledge, Bear is the first second order algorithm which achieves this sublinear memory limit. We did a small scale simulation on data generated from a normal distribution to recover sparse feature vectors beta star. We compared the probability of finding the support set successfully while changing the compression factor, which is defined as the ratio of the problem dimension to the size of the count sketch. The simulation shows that Bear achieves a significantly better phase transition curve compared to the first order Mission algorithm and performs fairly closely to the non-scalable version of Bear, which uses exact Hessian instead of the LBFGS approximation. Also, as a natural consequence of second order gradient step, Bear is less reliant on the choice of the step size parameter. Finally, we evaluated the performance of Bear on 4 real-world experiments with ultra high dimensional space, We observed that BEAR consistently outperforms mission and other computing algorithms, such as feature hashing, both in terms of classification and feature selection performance. In particular, the performance gap increases for larger compression factors, highlighting the power of BEAR in memory-constrained environments and regimes. To summarize, we have revealed yet another important implication of second-order optimization in large-scale machine learning. In addition to enabling faster convergence rate, superior computation communication trade-offs, and less reliance on the step size parameter, in this talk, we discuss how second-order optimization can be used to efficiently sketch the gradients in high dimensions to improve the memory accuracy trade-off in resource-limited environments. While we focused on massive dimensional linear classifiers to develop the theory around the algorithm can also be extended to training nonlinear models, such as a neural network with large number of parameters. Adaptive and distributed extension of BEAR are also interesting future directions to be explored in future. So with this, I want to thank you for listening to the talk and invite you to check out our paper using the following links.